Ferromagnetism. Ferromagnetism refers to materials that still possess magnetic properties even in absence of an external magnetic field. The electrons will create a strong magnetic field, and usually the electrons will cancel each other out. This does not happen with ferromagnetic materials, as unpaired electron spins will line up parallel to each other to form a domain, which is a region in which the magnetic fields of atoms are grouped together or aligned. A spin is a form of angular momentum carried out by elementary particles with their structure unknown. Even though the magnetic fields usually cancel each other out, ferromagnetic materials can remain magnetized after being subjected to an external magnetic field. This process is called hysteresis, a phenomenon in which the value of a physical property lags behind. This can be used, for example, in the basis of data storage in audio and videotapes. When the magnetized sections are moved under the playback, the moving magnetic field induces small currents, which is then amplified and turned into music. This would not be possible if the domains were not able to remember the magnetic field applied to them. Magnetic domains will not be altered unless acted upon by an external force, such as thermal regulation. This is why increasing the temperature makes a substance lose their magnetic properties. Antiferromagnetism. This is a property found in some metals in which the atomic magnetic moments, a quantity that determines the torque the magnet will experience in an external magnetic field, at low temperatures, form an ordered array of ions which are antiparallel, so it gives almost no external magnetism. Similar to ferromagnetism, but the electrons spin point out in opposite directions. Antiferromagnetism will turn to paramagnetism if it reaches above the Néel temperature, as the thermal energy is big enough to disrupt the pairing. Paramagnetism is when certain materials are weakly attracted by an externally applied magnetic field, and it forms internal magnetic fields. It does not retain the magnetism. The Néel temperature, analogous to the Curie point, depends on the substance and is named after French physicist Louis Néel, who discovered the form.
Altering temperature. At average room temperatures, magnetic moments of elementary particles will align, causing ferromagnetism. High temperatures can cause magnetic moments in magnetic materials to align randomly. Heating a magnet past the Curie point will result in a permanent loss of ferromagnetism. Curie point. Discovered by the French physicist Pierre Curie in 1895. This is the point at which materials will lose their permanent magnetic properties. Materials will only be ferromagnetic below their Curie point. This isn't an issue for ferrite magnets with a Curie temperature of 300 degrees Celsius, but this is an issue for strong neodymium magnets whose Curie point is only around 80 degrees Celsius. The Curie-Weiss law shows the magnetic susceptibility chi of a ferromagnet in the paramagnetic region above the Curie point. It is described as chi being equal to C divided by the quantity of T minus T sub C, where C is the Curie constant and T minus T sub C is how high above the Curie point the temperature is.
Magnetic domain and electrons. The magnetic moment of a magnet is the quality that determines the torque it will experience when acted upon by an external magnetic force. The torque causes a spin on the electrons within the particle. Electrons within a magnet commonly maintain a parallel aligned spin, thus making them magnetic and giving them positive and negative poles. When a magnet is heated to its Curie temperature, the spins on the electrons within the material will become unstable and the material will lose its magnetism. Unless an external magnetic field is present to realign the spin on the electrons, the materials will cool with the electrons disturbed and it thus loses its magnetism. An example of this is paramagnetism, while ferromagnetism is a material with all of its electrons still aligned, and therefore it's magnetic.
The effects of heating magnets. This is a visual representation of the magnetic field prior to heating the magnet past the Curie point.
By heating the magnet past its respective Curie point, 80 degrees Celsius or 353 Kelvin, the spins of electrons in the magnet align randomly, causing the magnet to lose its magnetic field.
This visually demonstrates that the heated magnet has lost its magnetic field.
This demonstrates that a control magnet is able to attach to and pick up the paper clips, but the heated magnet is unable to.
Fiend.